Hello everyone and welcome to this session on basic statistical calculations. My name is Vamsidhar. As a part of this session, let's look at some of the most common calculations which people tend to do for making a statistical analysis. The two major aspects that would be looked at, one is a measure of central tendency. There are 4-5 mechanisms we will discuss on various measures of central tendency, and we also talk about the different measures of dispersion or variation. If you remember, in one of our earlier chapters, we have discussed that there are 5 characteristics to a data, and the first two of them being the centeredness of the data and the dispersion in the data. So in this chapter, we will be focusing on how do we measure the centeredness of the data as well as the dispersion that is present in the data. So let's start looking at these two key aspects in this chapter. So moving further, when we talk about the measures of central tendency, which talks about what is the value which represents the center or the middle of my data set. What is that particular value that represents the middle or the center of my data set? What is that representative value? So there are multiple mechanisms to determine them. The most common things which people use are the concepts of mean, median and mode. These are the three different ways of defining the centeredness of a particular data. And as we all know, mean is the most common out of those three, which is nothing but people also use a word called average for that. Average is nothing but the sum of all the data values. If you are given a data values like 1, 2, 3, 4, 5 being the 5 different data values, the sum of all these data values, which is 15, divided by the count 1, 2, 3, 4, 5, the count of the data values, which will give me the mean. So the way the mean is computed is all the data values that you have, you sum them up and you divide by the total number of values, which will give you the mean value. And depending on whether we are computing the mean for a sample or a population, the terminologies differ. When we are computing the mean of a sample, we call it as x bar. When we find the mean of a population, we represent it as mu. The terminologies also should be slightly comfortable for us. Whenever we see x bar, it means that it is representing a sample. Whenever we see mu, we can very well say that it represents a population. So the sum of all the data values divided by number of elements in the sample, which is represented by small n, or the number of data points in the entire population represented by capital N. So that is what is the definition of the mean. So whether we are using a sample or a population, the calculation remains the same. The sum of all the data values divided by the total number of data values. And some of the advantages people look at with the usage of mean is relatively reliable, because any calculation which we make, there should be a lot of reliability to the calculation. What it says is, if you are taking up a good sample size, which is more random in nature and all those characteristics being satisfied, whatever is the different sample that we are taking, the mean of the sample is more and more consistent compared to the other measures. So if I am taking out of a population of 100, if I pick up some 10 of them randomly and try to find out the mean, and some other 10 randomly and try to find out the mean, the means will be more or less closer enough. compared to the other measures like median or mode. So that is one prime reason why people look at mean as a better measure compared to a median or mode. But however, mean also has some disadvantages. On a positive note, mean takes every data value into account because it is adding all the values. Each value will have an importance in the calculation of the mean. But that itself is a disadvantage also. If one of the values is extremely large or extremely small compared to the others, which means if that one value or few values are outliers, the mean will get influenced heavily because in the summation, that particular value will have a very high influence because it is very extreme. The summation will have an impact, and as a result, the mean also will get badly impacted. That is why we call mean is a non-resistant measure. What do I mean by this word non-resistant measure? It cannot resist the change if one value is extremely distorted. So it is very sensitive to the outliers. So that is one negative thing that works for the mean, but otherwise because of its heavy reliability, we use mean more compared to the other modes of central tendency. Then looking at the median, the way median decides the center, the way mean decides the center is you add up all the values and divide by the total number of values, which will be the center. Whereas the median defines center as you arrange all the data in either the ascending order or the descending order, pull out exactly the middle value. In that, the procedure it says is first sort the values, either in the ascending or in the descending. See how many values are there. Is the total number of values odd? 1, 3, 5, something like that? Or is it even? If it is odd, then pull out the value which is lying exactly in the center of the data set. That is what is called as a median. Whereas if the total number of values is even, for example, if my data set is 1, 2, 3, 4, 5, I have arranged them in the ascending order. The exact middle one, which is this one, is what I call as the median. But if my total data set contains even number, there are 6 number of values, then my median will be the average of the middle two because I will not have one single middle. So I will have the mean of the middle two, which will result in 3.5 being the median in this case. So there are two ways of deciding the median depending on whether my total data is odd or even. If my total number of data points is odd, directly you can pull out the middle value and call it as the median. If the total number of data values is even, you try to find out the average of the middle two values and you can call it as a median. One thing we have to keep in mind, we are always using the word called average for calculating the center. Whenever we say center, we used to use the word called average, but please not use that particular term called average. Whenever we talk about the centeredness of the data, use the measures as mean, median or mode rather than using the word average. Though average will refer to mean, but it's better to avoid the term called average. It's better to use terms like mean, median or mode. And when we come to mode, this is the other way that it defines the centeredness of the data. It simply says the value that occurs with the highest frequency. The value that occurs many number of times, maximum number of times, out of all the other possible values is what is called as the mode. But what is the problem with this? In some cases, there could be two different values that can come with the greatest frequency, same frequency, but the highest frequency. Let's say there could be a number 10 and there could be a number 20 which are occurring 10 times each in the data. Then what is happening is that particular data set can have two modes. And we call that particular, because the way we are defining The mode is the number which repeats maximum number of times in a data set. So there could be a possibility of two numbers repeating maximum number of times, in which case we call it as bimodal. If there are multiple numbers that are repeating maximum number of times, then we call it as multimodal. If more than two, any number of data points repeating maximum number of times, we call it as multimodal. And when no value is repeating maximum number of times, there is a possibility of a no mode also. And because of this reason, some data points may not have a mode at all, and some other data points may have multiple modes also. It is because of this reason mode is generally not considered as a measure effectively. The reason being, for some data points I may not even have a mode at all, so my analysis will get distorted if it does not have a mode. So that's where people stopped using the concept of mode for quantitative data. In most of the cases, mode is being used only for qualitative or categorical data, typically the data which is having a nominal level of measurement, male and female, how many quantities of each of them. So mode is generally associated with a qualitative or categorical data, because for categorical data I cannot use a mean or a median at all. So only the counting of the frequencies is the only thing that can be done with respect to categorical data. So mode is the only measure with respect to the categorical data. So especially when I am using categorical data, mode is a measure of the center, whereas I will not use mode for quantitative data. Mean and median are the better tools for quantitative kind of a data. And there is also something called mid-range, which is nothing but the average of the maximum value and the minimum value, and it takes only two data points. This is one of the drawbacks of using the mean or the mid range. In the mean we are using multiple data values, whereas in case of mid range only two values are being used. So it is very sensitive to the extremes, because it takes only the maximum value and the minimum value. If the maximum is an outlier value, or if the minimum is an outlier value, immediately mid-range is getting affected in the calculation heavily. So though mid-range is a measure of central tendency, people don't use it for measuring the center, because of one, it uses only two data points, and because of that it is extremely sensitive to the extreme values. Yeah. Now some other calculations wise, sometimes there is a possibility that we may end up finding out the mean for a frequency distribution, not for a data. So just if I have to look at the scenario of the earlier data set, wherein we were computing the pulse rate. So just to tabulate it again, 60 to 69, 70 to 70, 80 to 89, 90 to 99, 100 to 109, and 110 to 119, and we have 120 to 129. The frequencies being 12, 14, 11, 1, 1, 0, 1. If this is the example we were talking of, and I have to find out the mean, so this is not a raw data. If I have to find out a frequency distribution, if I want to find out the mean for this particular frequency distribution, then all we need to do is, the first step, take the midpoints of each of the classes, 64.5, 74.5, 84.5, and so on. Then multiply the frequency with the corresponding mid value. So for each of the classes, I will get the mid value multiplied by the corresponding frequencies. So these are the values I will get. Then add up all these values, and whatever the value that I get, divide it by the total frequency. Here the total frequency is 40. and that is what we get as the mean. And that is what we call as the weighted average, weighted mean. What do we mean by weighted mean? I am not taking the mean of the mid points directly. I am multiplying each midpoint by its corresponding frequency and dividing by the total sum of all the frequencies. Here also, if we see the expression, if I want to find out the mean of x, I am not directly finding out the mean of x. I am multiplying each x with its corresponding w, which is its corresponding frequency, and dividing the total by the summation of all the frequencies, which is the summation of all the weights that are assigned. So the way we are computing the mean of a frequency distribution is also called as a weighted mean. The typical mean is a simple average of the existing data point. But if I multiply it with their corresponding frequencies and divide by and add up the total and divide by the total frequencies, it will boil down to a weighted mean. So that's also one more way we end up doing the central tendency calculation. So we have to be comfortable with all these types of calculations. Then there is one concept with respect to the mean median mode. The moment for a particular data set, I look at the mean, median and mode, it gives me an indication of what is called as skewness in the data. Skewness is a measure of symmetricity in the data. Is the the lower 50% a mirror reflection of the higher 50%. If I am trying to plot a frequency distribution, is there any kind of symmetricity in the data, which means the lower 50% of the data, is it more of symmetric or a mirror reflection to the higher 50% of the data? So the data is more skewed if it is not symmetric. That's the word we use. If the data is not symmetric, then we call as skewed, which means either it is extending more on one side compared to the other. If it is symmetric, the left hand side should be a reflection to the right hand side. Otherwise, we call either as negatively skewed or positively skewed. When I say negatively skewed, the tail is pretty long towards the left. We'll see in the next slide. The typical frequency distribution graph may be like this, where the tail is pretty long towards the left, and we see as a calculation mean and median will be to the left of the mode. Whereas in a positively skewed, we see that the frequency distribution is more extended to the right, which means the mean and median are always higher compared to the mode. So in a skewed distribution, this is the typical kind of setup we will see. If the distribution is more or less symmetric, like this, you see the left hand, the one towards the left is a reflection to the one towards the right. And one more thing which we observe is this is the point which is the mean, the median as well as the mode. One single point will represent all the three. That is what we'll talk about symmetricity, or that is the point where we say skewness is equal to 0. Whereas in this case, where we are seeing that the tail is elongated towards the left, we have a big tail in the left, whereas not much of a tail to the right. Such kind of situation is an indication of negative skewness or left skewness, wherein what we are seeing is the mean and the median are towards the left of the mode. Mode is a point where there is a peak because it's the one that occurs with maximum frequency. So what we will see is mean and median will be lesser compared to the mode. There may or may not be any order between mean and median, but they will definitely be lesser than the mode in case of a left skewed or negative skewed distribution. But in case of a positive skewed distribution, we see that the mean and the median will always be to the right of the mode. So this is the kind of a pattern we can analyze just by knowing mean, median and mode for a data set. We can say whether the data set is more or less symmetric about the mean, or is it more skewed towards the left or more skewed towards the right. This one more interpretation we can do from the data set directly. Now that we have looked at the measures of centeredness of the data, now will move on to look at the different measures we use for measuring the variation in the data. What is the measure of dispersion in the data? Sometimes people also use this as a measure of dispersion. How much is my data dispersed? So there are again different tools for it, different formulas. The most commonly used formulas are range and standard deviation, whereas there is another tool called mean absolute deviation also for it. Now, how do each of these things measure the dispersion? Range, it's nothing but it takes only two data values, just like your mid-range. The range is a measure of dispersion which takes only the maximum data value and the minimum data value and does a simple subtraction between them. So the higher is the range, the higher is the dispersion, and vice versa. Because it is very sensitive to the outliers, because it depends only on two values. It does not take every value into consideration. The range is computed just with a very high value and a very low value. So though it is easy to compute, it's not heavily used, because one, it is relying on only two data values, and the moment one of them becomes a very heavy outlier, the range gets very badly impacted with it. So very common measure is people ignore the range for measuring the dispersion in most of the application. Then the next alternative is standard deviation. And something which we have to remember for standard deviation is the simple way to define the standard deviation is mean of square of deviations from the mean, or probably let's write it as square root of mean of squares of deviations from the mean. That is what is the better way to represent standard deviation. Now if you look at each of the aspects, square root of mean of, because I have to take the mean, squares of the deviations from the mean. So I am trying to find out the mean. If I am doing it on a sample, the mean is x bar. If I am doing it on a population, the mean is mu. So what we are saying, deviations from the mean, each value, how much is it deviating from the mean, square of that deviation and the mean of that. Mean of the square of the deviations from the mean is, and the square root of that resulting value is what we call as the standard deviation. And there is a difference in the standard deviation of the sample as well as the population. You see the denominator that is used to find out the mean. N minus 1 is used in the denominator to find the mean of the square of the deviation, whereas n is used in the denominator in case of population. We'll discuss about why n is used for population and n minus 1 is used for a sample to find out the standard deviation slightly in the another two slides. But the way we are calling as the average dispersion of every value from the center is what we call as the standard deviation, and it is done through this mechanism. And if I don't take the square root, or the square of the standard deviation, is what I call as the variance. There is not, whether you do it for a sample or for a population, doesn't matter. If you are squaring the standard deviation, we call it as the variance. And any time we are using the technology of sample data, we should be very comfortable that the formula which we are using is the sample standard deviation, not the population standard deviation. There is always a point to be kept in mind, because whenever we deal with the sample, we have to use the formula that corresponds to sample standard deviation only and not the population. And there is one more measure, as I said, it is the mean absolute deviation. So, as the formula is saying, it is also called as the mean of absolute deviations from the mean. So, every value we are finding out the mean of the sample, finding out how much every value is deviating from the mean, take the absolute of it, add up all the deviations, absolutes of the deviations add up, and find out their average by dividing by the total number. This is what is the mean absolute deviation. But in general, what we see is standard deviation is a more preferred measure compared to mean absolute deviation to talk about the dispersion, because mean absolute deviation uses a context called absolute, and absolute is actually not an algebraic tool. Typically, addition, subtraction, multiplication, division, square root, square, cube, powers, these are the ones that become algebraic notation, but absolute is not a measure of algebraic. And because of that, in future, when we have to make some conclusions based on these calculations, it becomes very difficult. This becomes a limitation factor for making some conclusions, which we will discuss at later point in time. But for you to simply understand this concept, because mean absolute deviation uses a concept of absolute, which is actually not an algebraic tool, we can algebraic notation, we cannot use mean absolute deviation, whereas the standard deviation uses square and square root, which are purely algebraic in nature. That is one reason people prefer standard deviation more towards the mean absolute deviation. And the use of any calculation, what should happen is, the different samples you are collecting, you should not get completely different values for the mean absolute deviation. In case of mean absolute deviation, we get the values which are very biased, whereas any kind of sample you take, the standard deviation values are more closer compared to the more concentrated compared to the mean absolute deviation values. And even from this standpoint, people prefer using the standard deviation over the mean absolute deviation. Then one more thing we have to understand is, in the standard deviation formula, especially for sample, we were dividing by n minus 1. The reason being, let's say you have n data points and you already know the mean. You have already estimated the mean, you know the mean. Now, if this mean is already known, you can freely change the values of only n minus 1 data, because the last one is purely based on this. It has to be an adjusting factor. It is an adjusting factor to produce this much of a mean, right? So only n minus 1 values are freely assigned any number, but the last value cannot be assigned freely any number. So from that standpoint, what is happening is that last number is not a data point anymore. It's an adjusted factor to produce your mean of x bar. So from that standpoint, because there are only n minus 1 independent values, we simply say in finding out the standard deviation of the sample, we divide the value by n minus 1 and not n. And in reality also, people started finding out, if n has been used, it has been underestimating the population variance, but if n minus 1 is used, it looks as if it was estimating the population variance more accurately. So even from an empirical or an experiential standpoint also, it is preferred to use n minus 1 in the denominator to arrive at the sample standard deviation or sample variance, but not n. One more thing that has to be kept in mind. And whenever we talk about a standard deviation, a few important points for us to remember. It's the variation of all the values from the mean, because we said mean mean of the squares of the deviations from the mean and the square root of the entire stuff. So it's a deviation of all the values and it's an average deviation of all the values from the mean. Generally it will be positive, it can never be negative. It can be 0 in some cases, provided all the values are the same number. Even if the one of the values is slightly different, standard deviation will exist and it will be a positive number itself. The higher the standard deviation is, we say that the variation in the data or the dispersion in the data is very, very large. And the value of the standard deviation, it will be very, very high. It's more and more affected by outliers. If your data has very high or very low outliers, of one on the very positive side or on the very negative side, if there are outliers in your data, standard deviation is very heavily affected by it. Just like because mean is affected heavily, the standard deviation is also affected, because the formula for standard deviation is nothing but deviation from the mean. So if the mean is affected, the standard deviation is also badly affected. Then the units are the same as your original data. So if your original data is in grams, the standard deviation also can be in terms of grams. Original data is in meters, the standard deviation also we can define it in meters. And whenever we have to compare two sample standard deviations, okay, this particular data's standard deviation is lesser than some other data's standard deviation. If I have to make such kind of conclusion, the first thing is it's always appropriate to make that conclusion, to make that comparison only if their means are more or less the same. Only if the means are more or less the same, then we'll use the comparison of sample standard deviation straightforward. Otherwise, there is another process which we'll look at slightly later. It is called as, we will take the coefficient of variation to compare the sample standard deviations in case their means are not the same. So as a practice, we have to remember, it does not mean that if one of them is having a standard deviation of 10 meters and the other one having a standard deviation of 25 meters, I cannot say that the standard deviation of the first one is lesser than or the dispersion in the first one is lesser than the dispersion in the second. That statement can be made only when their means are approximately the same. If they are different, then we have to resort to this calculation of coefficient of variation, not the direct standard deviation. And for most of the data sets, we say a particular value is unusual or an outlier. For any data set, in most of the cases we make this statement, this particular value is unusual or outlier if it differs from the mean by more than 2 standard deviations, either on the higher side or on the lower side. If it differs by more than 2 standard deviations, we try to call it as unusual, or sometimes we call it as outlier. So these are some of the important things that we derive by looking at the standard deviation. So as a part of analyzing the data, standard deviation forms one of the key aspects for an analyst. So just as a quick summary of how we are finding out the standard deviation, for any data that is given, first compute the mean of that, then subtract the mean from each of the individual values, separately, then do the square of those subtractions, add up all those squared subtractions, for that total divided by n minus 1, and whatever the result that comes, take the square root of that. That is what will result in the standard deviation for your sample. Then, how do I use the standard deviation for interpreting the shape of my data? If at all I see that my data is a bell-shaped or a symmetric kind of a distribution, these are already empirical, which means they are already observed for a data which is following a bell-shaped, or earlier we have defined that this kind of a distribution is a normal distribution. What we see is from the mean to plus or minus 1 standard deviations, we see approximately 68% of the data lies between that. 34% on the left and 34% on the right, because a bell-shaped standard normal distribution is more symmetric in nature. So approximately 68% of the values, if they lie between plus or minus 1 standard deviation of the mean, then we say that that distribution is a bell-shaped distribution. Similarly, around 95% of them should lie between 2 standard deviations of the mean, and close to 99.7, very close to 100. Almost 99.7% of the data should lie between plus or minus 3 standard deviations from the mean. These are the rules that are applicable. So that's how we use the standard deviation to predict the shape of the data, the shape of the distribution of the data. One example being a bell-shaped or a normal distribution. If I observe that this much proportion of the data is lying between 1 standard deviation, 2 standard deviations, and 3 standard deviations from the mean, I can very well classify that that distribution is following a bell shape or a normal distribution. But for any other distribution, some of the things that we have to keep in mind, this rule that 68, 95, 97, 99.7 will be applicable only to a bell-shaped kind of a data. But for any kind of a data, if I have to say, there is a theorem that has come into picture which is called as the Chebyshev's theorem, or sometimes people call it as Chebyshev's inequality. What it says is, if at all I want to find out what is the minimum proportion of values lying between plus or minus k standard deviations from the mean, I say that that value is equal to 1 minus 1 by k squared. If I want to say plus or minus 2 standard deviations from the mean, then I will write it as 1 minus 1 by 2 squared, 1 minus 1 by 4, which is 3 by 4, or 75% of my data should mandatorily lie between plus or minus 2 standard deviations from the mean. For any kind of a data, the minimum number of data points that should lie between 2 standard deviations from the mean is 75%. But if it is bell-shaped, yes, 95% of them will lie. But if it is any other shape, minimum of 75% should lie. So we can easily, if it is 3 standard deviations from the mean, again I can do it as 1 minus 1 by 3 squared. So 1 minus 1 by 9, making it 8 by 9, or approximately around 88-89% of the values will definitely lie between plus or minus 3 standard deviations. So it only talks about a minimum value, lower limit, 89%, at least 89% will be lying. So it could be 90, 95, 99. As in the case of a bell-shaped curve, we have seen 99.7% of the data will be lying. So that's one more. This is one more theorem which says what is the minimum proportion of the values that lie between plus or minus k standard deviations from the mean. But the rule is valid, the formula is valid only if we are talking of at least more than 1 k standard, more than one standard deviation from the mean. If the value of k is 1 or less than 1, this formula will not be applicable. And then earlier we have discussed, if at all I have to compare two standard deviations, if they have the same mean, approximately the same mean, then I can directly look at their standard deviations and say one is having more dispersion compared to the other. But if their means are different, then the comparison is more appropriate using the coefficient of variation rather than a simple standard deviation. Coefficient of standard variation is simple standard deviation relative to the mean. Take the standard deviation by mean into 100 and arrive at the coefficient of variance, and then compare it at a coefficient of variance level, not just at a standard deviation level. Whether it is for a population or for a sample, doesn't matter. But if the means are different, take the standard deviation as a percentage of the mean, and after that do the comparison. So if the coefficient of variance for the first data is 20%, whereas for the second it is 40%, then you can very well say that the first data is having a lesser dispersion compared to the second, or vice versa. Then one more aspect we need to be comfortable in this context is the standardized value of a data. The standardized value of a data is nothing but z-score, very commonly used. And what we are doing as a part of the z-score is, any particular value I am taking, x, this score will give me by how much standard deviations is it above or below the mean. Right? Let's say the mean value is 20, the standard deviation is 5, and I am considering a value as 30. A particular value is 30. Then 30 is differing from 20 by 10 units. 30 is more than 20 by 10 units. I'll not name it as 10 units, but because the standard deviation is 5 units, I'll say 30 is more than the mean by 2 standard deviations. I'll not say by 10 units, I'll say that it is more than the mean by 2 standard deviations. I'll express everything in terms of number of standard deviations away from the mean. That is what is called as a z-score. And the way it is calculated is, you take for every value, you subtract the mean of that, whether it is a sample or a population, does not matter. You subtract the mean from that, and from the resulting value you divide it by the corresponding standard deviation. If my z-score for any particular value lies between -2 and +2, we call them as ordinary values. But for any specific value, we see that the z-score is above the limits, we say that it's an unusual value or an outlier kind of a value. So this z-scores really help us in deciding what are ordinary or acceptable kind of values and which of them are unusual. Anything below -2, any z-score above +2 will fall into an unusual or unacceptable kind of values. So typically if any value is greater than the mean, the z-score will be positive. If any value will be lesser than the mean, we see that the z-score will be negative. So just as an interpretation, if I get a z-score is 2, the simple way to interpret is that particular value is 2 standard deviations above the mean. 2 standard deviations greater than the mean. That is a simple way to interpret a z-score. We'll use the z-score very heavily as a part of our inferential statistics when we have to make conclusions about the data as a part of chapters like hypothesis testing. So in that context, we'll use the z-scores more heavily in future. But just to understand, z-score is a way to standardize your data, irrespective of whatever is the mean of your data or standard deviation of your data. you are converting it into a standardized value. If the z-score lies between -2 to +2, we say that that particular value is normal, otherwise it is abnormal. So that kind of standardization is what you are bringing into your data analysis. That's the reason z-scores form a very important aspect of the statistical analysis. Then we also have to deal with some other aspects in this chapter, which is partitioning of the data into more than two groups. Partitioning of the data into two groups, and what value partitions the data into exactly two groups, we said it is median. But if the entire data has to be partitioned into four equal parts, where 25% of the data lies in each of the parts. So what is this value which divides the total numbers into 25% towards the left and 75% towards the right, or 75% towards the left and 25% towards the right? Not just the median, which is a central cutting, but I want to cut the data into two parts, where the left part will be some proportion of the total data element and the right portion is some other proportion. Such kind of tools are called as quantiles. Any cutting of the total data set into two parts, where the left part of it is some percentage of the total and the right part is some other percentage, number of values in the group wise. So the most common tools that are used as a part of the quantiles are percentiles, where you divide the total number of elements into 100 groups, and each group will roughly represent equal number of elements. Let's say if I have 1000 elements, and I have to, if I am talking about a percentile, it's as good as the 1000 numbers I am breaking into 100 groups, and each group will have approximately 10 numbers. That is what we are calling it as a percentile. So given any value, if I want to find out the percentile of it, the simple way is find out the number of values less than the x. If I am having 1, 2, 3, 4 up to 100, if I want to find out 98, what is the percentile corresponding to 98? How many values are less than or equal to 98? There are 98 values which are less than or equal to 98. By total number of values 100 into 100, which says this is the 98th percentile value. That is the way people try to find out the percentiles. In most of the exams also, in competitive exams, people will get what is called as a percentile number, which is exactly calculated by this formula: number of values that are lesser than that value divided by the total number of values. And similarly, if I break the whole data into four groups, where one group is 25% and the other 25% of the total values, and the right side group contains 75% of the total values. The Q1, when I say first quartile, it separates the bottom 25% of the values from the top 75% of the values. If I say Q2, which is, it separates bottom 50% from the top 50%, which is as good as median. If I say quartile 3, it separates bottom 75% from the top 25%. So like this we define the quartiles. And whenever we talk about interquartile range, the most common calculation is Q3 minus Q1, and semi-interquartile range goes as the average of the Q3 minus Q1, and the more other calculation which is generally done is mid-quartile range, which goes with the average of Q3 and Q1. These are the three most common calculations which are done with respect to quartiles per analysis of our data. Then one more thing that talks about the presentation of the data is what we call as a 5-number summary, wherein for each data we compute these 5. The first and the last are quite easy, the minimum and the maximum value. Then we compute the first quartile, the second quartile, which is the median, and the third quartile. As we said, how do I find out the quartile? You arrange all the data in the ascending or in the descending order. Take that particular value where 25% of the 25% of the values will be on the lower side of it and 75% of the values will be on the higher side of it. Or the simple way, the calculation way of finding out your Q1, Q2, Q3 is you whatever, if there are n data points, take n plus 1 by 4th element. This will become your first quartile value. 2 into n plus 1 by 4th element, which is n plus 1 by 2th element, will become your second quartile or the median. And 3 into n plus 1 by 4th element will become your third quartile. And if the values are not directly possible, then you are taking the interpolation, which I'll discuss in a short while from now. So once we find out the Q1, Q2 and Q3, we know the minimum and maximum value. These are the 5 things that summarize the data with respect to the outliers. We'll see how it works out. This is typically, these 5 values are typically used to construct what is called as a box plot. The box plot looks something like this, wherein these 5 are plotted in this manner. The five numbers: minimum, Q1, Q2, Q3 and the maximum. And what we do is we create a box which contains, the box is between Q1 and Q3 and median is driven as a line within that box, right? So Q1, Q2, Q3, these 3 are there, and the minimum is plotted with a horizontal, is plotted with a line, and maximum is plotted with a line. These two, minimum and maximum, are typically called as whiskers, and there is a smooth straight line that joins from Q3 to maximum and Q1 to minimum. This typical kind of a plot is called as the box plot. Why are we using this box plot? There is an immediate meaning for me, which is saying between Q1 and minimum there are very less amount of values, whereas from Q3 to maximum there is a big gap. Q1 to minimum there is a small gap, Q3 to maximum there is a big gap, which is saying there is a big dispersion in the about 25%, in the highest 25% of the values, but not too much of a dispersion in the lowest 25% of the values. And the other way you see is between Q1 and Q2, you are finding a lesser gap, whereas between Q2 and Q3 there is a bigger gap. Even that also suggests that there is a good amount of dispersion above the median, but below the median the dispersion is much lesser. So there is a wide spread in the values on the higher side, but there is not big spread in the values on the lower side. So such kind of conclusion can simply be made just by looking at your box plot. So we can make a good analysis on the centeredness, or as well as the spread in the data, just by looking at the box plot. So people use box plot for understanding the centeredness as well as the spread in the data. But sometimes it's also used to identify the outliers. The way people have modified the box plot for the identifier purpose is, they have taken the minimum and the maximum. Instead of taking the minimum and the maximum of the data, what they have done is, for minimum they have gone with Q1 minus 1.5 times interquartile range. Whereas for the maximum they said Q3 plus 1.5 times interquartile range. If my actual data value is below this minimum or above this maximum, they are calling it as outlier. And some softwares, they have even started showing some special symbols like star for those kind of values. So the box plot, they have modified the traditional box plot. Instead of taking the minimum and the maximum values from the original data, they started considering minimum means the q1 minus 1.5 times the interquartile range. The maximum means q3 plus 1.5 times the interquartile range, and then use that to plot your box plot. And if your actual value, any data value or values, is either lesser than this artificial minimum or artificial maximum, they started identifying them as outliers. So because the box plot, now the modified box plot can identify your outliers very significantly, there is a lot of popularity today for the box plot. The box plot is helping people to identify the outliers and remove the data effectively. So that's the reason box plots are becoming heavily popular for the statisticians today. Just by looking at it, and with the advanced tools, they can get all the stars which will say that these values are outliers in the data. So without they manually identifying what are the outliers in the data, just by plotting a box plot, they are able to identify that these particular values are outliers in the data. So the horizontal lines which were at this 4.5 and 225 in this particular data, they will not be at 4.5 and 225. A new value will be created. For the same example, if I have to talk about, the interquartile range is 113 minus 35. 113 minus 35 is 78. So the interquartile range is 78. So I'll say the minimum, the artificial minimum is Q1 minus 1.5 times interquartile range, and the artificial maximum is 113 Q3 plus 1.5 times the interquartile range. So it is some negative value here, whereas here 78 plus 39, 117 plus 113, 230. 230 is my artificial maximum. Since no value is lying outside 230, I don't because the maximum value itself is 225. But if there is any one value that is lying outside 230, then we definitely call that to be a outlier, right? So that is what is an outlier analysis that can be done using a box plot quite effectively, right? So in this chapter, the whole focus was primarily on computing the mean, the median, the mode, which are the measures of central tendency. Then we were looking at measures of dispersion using range, standard deviation, mean absolute deviations, and then proceeded towards computation of quartiles, percentiles kind of stuff, and then focused on the box plot. How do I identify the outliers using the box plot? And there is a focus towards Z scores. How do I use the Z scores to identify unusual or extreme or outlier values, and how do I identify the normal values? And how the standard deviation can typically help us in terms of identifying the outlier. So in this chapter, the more focus has been, or if how do I look at the standard deviation to identify the distribution in the data. One is an empirical bell shaped kind of a distribution, and we also looked at a Chebyshev's kind of a theorem. So if you have any further questions regarding the measures of central tendency or a dispersion or the use of standard deviation or box plot, please feel free to get back to me on the phone number given below, 98480 12123. You can even drop in an email at vamsidhar@pacegurus.com, and I request you to visit my website www.pacegurus.com for any further clarifications or getting an updates regarding the various training programs we offer in the area of finance, analytics, and statistics using tools like Excel, SPSS, and VBA. I hope the entire session is self-explanatory. Thanks a lot for listening to this session. Thank you very much.